Hello, what is going on, ladies and gentlemen? It is Jake coming back at you with a technical interview essentials video. Today we're talking about trees. The wonderful tree. Look at that guy. Oh man. So why is the tree cool? We're just gonna go straight into it, guys. It's gonna be a quick video. Don't even worry about it. But the tree. When we think of a tree, we're kind of thinking usually of some sort of structure where, we have a root and we have some children, some leaves that just keep going down, whatnot. This is obviously a binary tree, but you can imagine that there could be, another node here as well, or something like that. Nothing too crazy, or something like that. What really makes a tree in its proper definition is a root node, or I guess it's a child will only have one parent. And so you can imagine that we have a root and we have a bunch of nodes, but all these nodes are unique in the fact that they have one singular parent. When we think about like a graph, if we go over here and maybe make a graph that's pointing to this node, who's then pointing to this node, we can make like a little circle here. One of the things that makes graphs interesting is the fact that we could have, let's say, two things pointing to one node, and that would have two parents being that node, or something like that. Whereas in a tree, we're only going to ever have one parent, which makes it kind of like trickle down, as we see here. But this tree in particular is not really special to us. I mean, sure, it looks like a tree, but this would not give the programmer any benefits. Like, why are we even making these tree structures to begin with? Well, when we make our trees, we don't want to make them in just any random way. We want to make them in a way that can be traversed in a log of n time. That is what makes a tree so powerful. When we think of our original array, we kind of have to search it, element by element, item by item, until we get to the end. So it's kind of like, you have to go through the whole thing. But with a tree, if we kind of ordered it or sorted it in a certain way, you could imagine that if I was looking for, let's say, this element here, I could just search 1, 2, and then 3 before getting to it. And if I was searching for this dude here, I mean, obviously it's just a little jump, but you could imagine that if this was stored in an array, kind of like so, and let's say that, we were searching for this guy right here, and let's imagine that this dude just represents the last element here. We only have to search, that 1, 2, 3 to get to it, instead of searching the entire array to get to the back. And for those that don't know, but just want to know what this log n is really saying, if n is equal to the size, so let's say here the size, if n for us I think is 7, so we have 1, 2, 3, 4, 5, 6, 7, but to kind of make this, let's say, unique, the log is really just the inverse of exponential equations, essentially, like that. So 2 to the 3 is 8. 2 times 2 is 4, times 2 is 8. We can see that. And then if we, take the log of 8, what we're trying to say, and there's like a hidden 2 here, I think, is the default value. But that could be anything else. If you made it in math terms when you're in math class. But for computer science, we just assume that it's 2 there at all times. And this is just going to equal 3. So what times 2 could give me 8, essentially? And that's going to be 3. And what this is basically saying is if we have an array or a tree of size 8, it is going to take at most 3 steps to find that element, which is super cool. And so the common types of trees when it comes to making our trees, one is the word balanced. When we say we have a balanced tree, essentially we're just trying to say we don't have a too terribly unbalanced tree. Is anything that can still satisfy the equation log n, log in a guy up here, would be balanced. Now, when we're doing complete trees, we want to, sort, or I guess make our tree nodes go from left to right. So when I'm inserting here, I'm going to keep going from left to right until there's an end. If I just made one here and got rid of these ones, that would not be a complete tree. We want to make sure it is complete from left to right. And the binary trees, we've been looking at binary trees the whole time, so we're not going to, kind of worry about that too much. It's kind of just a tree that has 1 or 2, 1, 2, or 1, 0, or 2 nodes. And so when it comes to our binary search tree, it's going to be a binary tree, but the way that we order this guy is going to be anything that's greater than the root, anything that's greater than the current goes to the right, and anything that's less goes to the left. And you can kind of see how if we had a root of 5, the starting node, if it's less than 5, it goes to the left, and if it's greater, it goes to the right. So we have 7, and then we say 6 is less than 7, so that would go kind of right here, as well as 8 is greater than 7, so it would be right there as well. So yeah, that's kind of a binary search tree. That's kind of what we're going for. And when it comes to traversing this guy, you're going to be, wanting to realize what is BFS and what is DFS and the difference between the two. When we're talking about BFS, this is really just a breadth first search. And essentially we just want to go in I think the trivial way, like how our minds would read it. It'd be 1, 2, 3, 4, 5, 6, ... Just keeping it going. And that would be the order of how you would traverse this tree. Traversing just means visiting all the nodes. And how you would implement this in code is we're going to want a queue. Obviously we could bring out the code and look at it line by line. I recommend just looking at a Geeks for Geeks page or maybe a different video on how to implement it. But essentially we want to use a queue, and we're just going to pop the root onto it, and we're going to put all the children onto the queue and kind of continue doing this until there's no items on the queue. And that would be a great way to implement BFS. Now DFS is interesting in the sense that we're just going to go straight down, kind of like so. 1, 2, 3. So we're just going to visit all the way down, and then afterwards we'll go to our 4 guy right here, and then we'll go 5, 6, and then 7, kind of like so. So with the difference between breadth first and depth first is that with depth first we're going to go straight down and then fill in the gaps, kind of going from left to right. That's at least the way that I usually implement my DFS algorithms. They could definitely go from 1 to go right and then kind of go left like so. That's definitely a way that could be done too. And the way that this is going to be implemented is usually through recursion. So you can imagine with the root, I'm just going to say, hey, visit my left child until it's null. So I visit here. Do I have another left child? I do. Okay, I'm going to go here. Oh, I don't have a left child, so I'm done. And once it visited the left, now we're going to visit the right. And then essentially that is how that algorithm would go down. But again, guys, this is just an essentials video. There's obviously more like B trees, red-black trees, and even sorting, like how to implement the sorting of a tree. But in my experience, this is really all you need to know when it comes to trees in a technical interview process. Yeah, I hope you all enjoyed. Thanks for watching. Peace.